In this lesson, we will study a special kind of exponential function and a special kind of logarithmic function called base e, exponential, base e logarithmic functions. To get us started with our lesson, let's really take a close look at what e represents. Now, I'll just go ahead and say e represents a number. So what number does the letter e represent? E is actually equal to this expression, 1 plus 1 over n to the power of n, as n gets bigger and bigger and bigger and bigger and approaches positive infinity. The mathematician named Euler plugged in n values, some integer values for n here, and he allowed n to get bigger and bigger and bigger. So he plugged in n equal to 1, n equal to 2, n equal to 3, and evaluated this expression. N equal to 100, n equal to 1,000, n equal to 1,000,000. And what he found was pretty fascinating. The larger that n became, this entire expression approached a certain number. This expression approached the number 2.7 approximately. So this expression did not really get any bigger than 2.7. Even for really, really large powers of n, this expression just kind of reached its maximum, if you will, or its peak, its threshold, at about 2.7. So for you and I in this class, we're going to say that e is approximately equal to 2.7. So what we're going to do is we are going to allow our exponential functions to have base e. Remember that exponential functions are functions whose base has to be a positive number and cannot equal 1. Hopefully you remember that from a previous lesson. Well, e is positive and it's not equal to 1, so our base is allowed to be e. When your base of your exponential function is e, you call it the natural exponential function. So this is the natural exponential function. Notice that our base is e. Now what we're going to do right now is we are going to graph this function, but I don't want you to lose everything that we already know about exponential functions, okay? Now we know a lot already because we've been working with them. For example, we know that if we let x be 0, we're going to get 1, right? This is the same y-intercept that's on all of our basic exponential functions. Remember, e raised to the power of 0 is just 1. Any non-zero number, and e is not 0, right? Any non-zero number raised to the power of 0 is just going to give you 1. So, but this doesn't surprise us because this is the same y-intercept that you and I were getting earlier. Furthermore, we get this, what I call a free point. If you let x be 1, you're just going to get your base right back, right? So 1 comma e is also a point on your curve. If you raise e to the power of 1, well, e to the first power is just equal to e. So here's another point that's on your curve. Now, when you and I were graphing exponential functions, at some point, you and I discovered, you know what? If we have just these 2 points, we can graph our curve. So these are the only 2 points that I will generate. Of course, you can generate as many points as you'd like. This function will be an increasing function because the base is more than 1. So we have 0, 1. We have 1 comma e. Now remember, e is about 2.7. So if I eyeball that, that's about right here, ladies and gentlemen. 1 comma e is about there. So remember, this is an increasing function. Also, do not forget, please, that your exponential functions, remember, they approach the horizontal asymptote, which is y equal to 0, the x-axis, right? So don't forget that that this curve cannot touch or cross the x-axis. So this is your natural exponential function. It's so it's such an important function because it has so many amazing applications in so many fields, especially in finance. This has major applications in finance, and hopefully in further lessons you will study some applications, some really cool applications about the natural exponential function. Now, let's talk about the natural logarithmic function. Now, this is f of x equal to ln of x. That's how you say that, ln of x. I always joke around with my students and I tell them, make sure you don't read this as one word like Linux, right? So I'm not sure if that's funny or not to you, but I think it's kind of funny. So please don't say, oh yeah, Professor Gutierrez taught me about f of x equal to Linux, It's ln of x, ln of x. This ln here, this is very important, means log base e, and then x is your argument. In other words, this function here really is or means the following: log base e of x, okay? So log base e, just this part alone right there represents ln, okay? Or ln represents log base e. So when you read ln, that means log base e. So obviously you don't see e here as a subscript. You have to understand that whenever you read ln, your base is e. It's a logarithm base e, okay? This is the notation for the natural logarithmic function. Now, I believe the root here, the root language here comes from Latin. And I'm not a very good Spanish speaker, but I do know that whenever you describe something, the adjective comes after the noun. And so just like in Spanish, the same thing goes for Latin. So this is, if this is going to describe the natural log function, you would think n should come first. So NL, right, of x, natural log, NL, but it's ln. It seems like it's opposite, and that's because of the root language that this comes from. It's logarithm natural, right? Logarithm natural. So the description of that logarithm, like what kind of logarithm, comes second. Just like you would in Spanish, like to say a red shirt, red shirt. In English, the adjective comes first, the describing part comes first, but in Spanish, which comes from Latin, the describing word comes second. So you would say camisa roja, right? The shirt red is the literal translation there. So anyway, I just thought that was interesting. Like some people ask, why is it ln and not nl, right? Natural log, nl of x. But it's because it comes from the Latin. I'm not sure if you found that interesting or not, or if you're gonna, log that away as useless information. I just think it's interesting why it's called ln. All right, so this is what I want you to remember. I want you to remember everything we already learned about your logarithmic functions, okay? We learned already that you have an x-intercept 1, 0. You don't have a y-intercept of 0, 1, right? That's for exponential functions. For log functions, you have an x-intercept, not a y-intercept, an x-intercept, and it's 1, 0. That is to say, if you let y, right, f of x represents y, if you let y be 0, x to the, not x, your base is e. I messed that up. The base is e. E raised to the 0th power, right, gives me 1. E raised to the 0th power will give me 1. So e raised to the 0th power gives me 1. That's how you read that. But this shouldn't surprise you, right? Because all of our basic logarithmic functions had this same exact x-intercept. The other point that you and I discovered and we called it, or I called it, the free point, right, is your base, comma 1. Your base is e, comma 1. So if you raise e, which is your base, to the power of 1, you're going to get e right back, okay? So these 2 points lie on our curve, and again, it should not surprise us because these are the same 2 kinds of points that you and I were getting when we were graphing our functions earlier. All right, so here we go. I'm going to graph our points. Now, remember that logarithmic functions have a vertical asymptote, and it's the y-axis. So this is x equal to 0. Your curve is not allowed to touch this vertical asymptote, and It's not allowed to cross it, right? So 1, 0 is your x-intercept, and e comma 1. Now don't forget, e is about 2.7. So 2.7 is about here, comma 1. So you're about right there, 2.7 comma 1, right? And we're approximating there. So here's your logarithmic curve. It looks the same as all of the other curves for your logarithmic functions. So as far as the graph is concerned, there's not much that's brand new here, okay? So please notice that it's following the same pattern as the rest of your basic logarithmic functions. Let's evaluate some log expressions. This is a natural logarithmic expression, okay? Now, I mentioned a little while ago that whenever you see ln, that means log base e, log base e. Also, please remember from an earlier lesson that a logarithm is simply an exponent. Once again, a logarithm is an exponent. So because this is a logarithm whose base is e, which you don't see, right? This subscript is invisible, but it is implied. ln means log base e. So really, if this helps you, I don't mind rewriting this. ln of e to the fifth power just means log base e of e to the fifth power, okay? So you have to see log base e whenever you read ln. So really, this is asking you, now get this, how simple this is. It's asking you for the exponent, because a logarithm is an exponent. It's asking you for the exponent to which you have to raise e in order to get e to the fifth. In other words, to what power do you raise e in order to get e to the fifth? What would this exponent have to be in order for this left-hand side to be equivalent to the right? That should be clear to you that e would have to be raised to the power of 5 in order to be equal to e to the fifth power. So the natural log of e to the fifth is just 5. Some students like to say that the natural log and this e kind of cancel each other out, and all you're left with is this exponent up here. Okay, that's true, but I'd rather you really understand, it's not that they're canceling each other out. I would really love for you to understand what this notation means. This new natural log expression says the natural log of the fifth root of e. Now, before we go any further, we already learned in this class that the fifth root of e is the same thing as e raised to the 1/5 power. Okay? Now, we also know that the natural log of e raised to the 1/5 power is basically asking you for the exponent to which you would have to raise e in order to get e to the 1/5 power. So I hope you see that you would have to raise e to the 1/5 power in order for u to be equivalent to e to the 1/5 power, right? So the exponent would have to be 1/5. If you raise e to the power of 1/5, you will get e raised to the power of 1/5. Next, we have the natural log of 1 over e to the fifth power. If you want, you can rewrite this as the natural log of e raised to the negative fifth power. You and I understood in an earlier lesson that a negative exponent like this will just reciprocate your base. So again, the natural log of e to the power of -5 really means to what power do I need to raise e in order to be equivalent to e to the -5th? Well, your answer is right there. If you raise e to the power of -5, you will get e raised to the power of -5. So your answer is just -5. I hope this is straightforward for you. Before we end this lesson, this relatively short lesson, I want to know if you can please pause the lesson here, pause the video, and evaluate each of these natural log expressions, and I will come back in just a minute and show you the value, okay? Show you the answers. So go ahead and pause the video here. Okay, I hope you paused the video and actually did this on your own. And I hope that you found that the answer for this, the evaluation of this expression here, the first one, is just 3. I hope you found that the evaluation of the second expression is -1. And I hope that you found here the answer is just 1/3. If this is, if these are the answers that you got for each of these expressions, then you understand how to evaluate a natural log expression, and it seems like you're understanding the meaning behind it. Now, if you did not get any of these answers, if you are struggling to understand, please allow me to elaborate one more time for you. The natural log of e to the third power is really asking you, to what power do I need to raise base e to in order to get e cubed? You would have to cube e in order to be equal to e cubed. So that's why that's 3. For this second expression, don't forget that the natural log of 1 over e is really the natural log of e to the negative first. So again, this is asking you, to what power do you raise e in order to get e to the negative first? Okay, so that's the reason why the answer is -1. And then finally, the cube root of e is the same thing as e raised to the 1/3 power. So this is asking you, to what power do you raise e in order to get e raised to the 1/3 power? Okay, so that's the reason why the answer is 1/3. All right, this lesson is relatively short, but that's what I wanted to show you. What do we mean by the natural exponential function? What do we mean by the natural log function, okay, which is ln of x? And I also wanted you to realize that the graphs of the natural exponential function and the natural logarithmic function follow the same pattern of our basic exponential and basic logarithmic functions. And also, of course, I wanted you to learn how to evaluate some natural logarithmic expressions. I'll catch you in a later lesson. See you later.